Hello, I have a new setup here. Do you like it? Anyway, let's start looking through this Unit 3B from 2019. Okay, so question 1, dead easy. Well, the first part anyway. So the current through a fixed resistor was measured as the potential difference across it was varied and the values obtained were plotted on this grid. First question is just to draw the best fit line, which was nice and easy. For B, part 1, you had to calculate the gradient of your graph using your best fit line and state the unit. So there's 3 marks, and this is what the marks are for. So first mark for picking out the correct points from your line. Remember, don't choose points that are plotted, choose points from the actual line of best fit. Just ones that are going through nice grid lines on the graph, don't choose random ones. Then for calculating your gradient correct from your point, and then one for the unit. This is a little extra note that I had put on for myself whenever I was marking this earlier on this year. So the unit for the gradient, they would have accepted either amps per volt or ohms to the -1. So you get that from your graph, because calculating the gradient you divide the y-axis by the x-axis. It's going to be the unit of the y-axis, which is milliamps, divided by the unit of the x-axis, which is volts. Now, if your number was in milliamps, like if you didn't account for this prefix in your calculation of your gradient, then this would be milliamps per volt. But if you did account for your for the milli in your numbers, then it's going to be amps per volt. So that's what I mean here with the way I've written in match to your numbers. If you've converted to amps, then your unit should be amps per volt. If you haven't, then it should be milliamps per volt. Right? Part 2. The manufacturer states the resistance of the resistor as 4.2 kilo ohms plus or minus 10%, and use the graph to confirm if the resistance of the resistor falls within the claimed range. So because it is an IV graph, the resistance is 1 over the gradient. So that's the first thing you have to calculate, and that's what the first mark is for. As long as that's consistent with your gradient, that's the second mark. Then you need to calculate 10% of this, so of the 4.2 kilo ohms, calculate 10%, figure out what range that is, and then see if your value is within that range. So depending on the value of your gradient, that means different people will have different answers here. Some people will be saying yes, it is within the range, and some people will be saying no, it's not. It just depends on the value of your gradient. Everyone's gradient should be similar enough though, because the line, like the points, did give a pretty good straight line. Right, let's look over. Let's see. So the ammeter used to obtain the values of current for the graph have a 0 error. What is meant by 0 error? It just means that it's the measuring instrument. So what is it in this case? It's the ammeter, isn't it? Yeah. It just means that the ammeter is going to have a reading on it before there's current going on it. So like if it was one of those wee analog ones, then the wee arrow or the wee pointer thing would be sitting not at 0 before it's even plugged into the circuit. If it is one of the digital ones, you know, sometimes you turn them on and it says like 0.02 or something like that, but it's not even in the circuit. That's a 0 error. It's not saying 0 when it should. So this is the mark scheme answer. So the meter has a non-zero current value when the current or potential difference is 0. For part 2, explain how the graph here indicates that there is a 0 error in the ammeter. So the mark scheme answer is that the graph doesn't go through the origin. So if you look back at your graph, see here the way hopefully your line of best fit doesn't actually go through the origin. That is implying that whenever there is, it must actually be reading off as a negative current. So whenever there's 0 volts, the current must be reading as like minus 0.07 or something like that, which is obviously not right. So there is a 0 error there. Then calculate the magnitude of the 0 error. It is the value of the y-intercept substitute that into y equals mx plus c, and then that is going to give you the, the value of it. Now, whenever I was reading that, I was like, oh, but sure you can't get the y-intercept, but you can get the gradient. You've already got the gradient from the graph, and if you pick a point on the line, like say I had picked, let's pick a nice one, say I picked that point there, then I would substitute in a voltage of 1.5, I've lost my point, here it is, and a current of 0.28. So that gives me my, I've forgotten what I said there, 0.4, 0.25? 0.15. So 0.15 equals whatever value I had for my gradient. The corresponding x coordinate was 0.28 milliamps, so times 10 to the minus 3. Oh no, because that's in milliamps, I don't need to times 10 to the minus 3 that. Plus c, and then you can solve for c. Oh, that was a wee bit messy the way I explained that, apologies. Right, so question 2. 2 light styrofoam balls are covered in a thin layer of aluminium foil and attached at either end of a string. The string is suspended from its midpoint and the styrofoam balls are given an equal charge of Q. They repel each other as shown. So I would be making note of this, sort of like a mental note of this in case this comes up later on. So it's one bit of string and L is half of the length, it's not the full length of the string. So if they're asking for the length of the string that's been used, you need to make sure that you're going to be doubling L. I don't actually know if they ask it, I haven't looked ahead. So it gives you the equation for the charge on the wee styrofoam balls here, tells you what everything stands for, and tells you what the value of that constant is. I think that's all we need to look at there. So the first question on this stuff, to find the charge Q, L is varied and the angle theta is recorded for each L value. A straight line graph is to be plotted that will allow a value of Q to be determined. Show that, I like it whenever it's a show that because then obviously you can get there eventually. So show that a graph of 1 over L against sine theta root tan theta will result in the straight line graph. So you can see here whenever I've been doing this, I've made a wee note of this is the y and this is the x. I have started out, as I always would, by writing out the question, or not the question, the equation that they give me, and then I'll look at that and think, right, I need to rearrange this to make it so that 1 over L is y for y equals mx plus c, and sine theta tan theta is x in y equals mx plus c. So if you can see here, this is what the marks are for. There's one mark for getting 1 over L on the left hand side and Q correctly on the right hand side. There's one mark for the full correct rearranging, and then there's one mark for mapping it to y equals mx plus c. So to get from here to here, we've divided both sides by L and we've divided both sides by Q. So dividing by Q leaves you just with 1 on this side and then 2 over Q here. And dividing by L then gives you 1 over L over here, and it disappears from this side. You will also notice as well that I have split this up into 2. So the square root here was originally mg tan theta over k, but because they've asked for it like this, I've just separated them out and like had them multiplying together. It means the same thing. So it's like what do you call it as surds, right? If you remember doing those, it's just like that, like separating out the stuff that is being square rooted. So the mg over k here has come out to here, and then I've just written these two beside each other. Hopefully you can follow that. Then for B, how is a value of Q determined from the graph of 1 over L against sine theta tan theta? If you just write like use the gradient or something there, you're not going to get that mark. But this is what you had to say to get the mark. So because if we look here, and I think I've written this out underneath here, we had, whenever we mapped to y equals mx plus c, we know the gradient is equal to 2 over q multiplied by root mg over k, right? So this is me working out here. So the gradient is 2 over q root mg over k. So all you need to do is rearrange and make q be the subject of that then. So I've multiplied up by q and divided by m, or the gradient, which takes me from this line to this line. So q is 2 divided by the gradient, and that's all getting multiplied by mg over k. Okay? Ooh. Right, let's look at number 3. I love wee questions like this, part A. So, figure 3.1 here shows a container of circular cross-section. Oh, that's sneaky. I would worry I would forget about that. Anyway, circular cross-section area A with a tube of cross-section area B, so it's this wee bit connected to it. A liquid added to the container will flow out through the tube. The time taken for the level of the liquid to fall through a height h in the container is given by this equation here. Now, tells you g is acceleration due to free fall. Show that the right hand side of this equation 3.1 has the unit of time, and it's stuff like this I do. I don't know why I love it so much, but going from here to here, all I've done is substituted in the units. So A, it told you, was a cross-sectional area, so that's going to be meters squared. B is also an area, so that's meters squared. Root 2, I wrote it in, but it doesn't have a unit, so that's why I've scored it out then eventually. H is the height, so that's meters, and G is G, so it's meters per second squared. So these cancel each other out. The 2 doesn't have a unit, so that's why it disappears. So you end up with the square root of meters divided by meters per second squared. Then obviously your meters are going to cancel. So you end up with the square root of seconds squared. And I've sort of jumped a little step there. Really, the step in between here would have been the square root of 1 over seconds to the minus 2. Which then, if you bring that up to the top line, becomes a positive power, which square root of second squared is just seconds. Okay, so there was 2 marks for that. Oh, I don't have room here, hold on. That's what the marks were for. There's one for substituting in all of your values correctly, so for substituting meters squared for A and B, for substituting meters for H, and for substituting meters per second squared for G. And then one for correctly cancelling it and getting an S, because they told you what you have to end up with. That's why all of this has to be done for 1, because you'll be able to manipulate it even if you've done it wrong whenever they've told you what to get. Does that make sense? I don't know. Okay, and another one that is actually secretly amazing, for part B, it tells you that the time taken was this. No, that's a lie. The height is that. The time taken is this, and the diameter is that. Calculate the cross-sectional area B of the tube and the percentage uncertainty, and it's the percentage uncertainty bit that obviously I am loving. But here's my solution. I'll go through my solution first, and then I'll tell you what the marks are for. Okay, so just substituting in the numbers to end up getting B first of all, so that's quite straightforward. 10.3 for T, 0.00727 for A, 2 times the height which they had given you in the question, and G is just 9.81. That gets you that value for B. Okay, then let's see, this here bit here, so I've worked down here and then gone down here. B equals A. Sorry, this is just me rearranging this equation and making B be the subject so that I can figure out what I have to do with the uncertainties to get it. So you end up, whenever you rearrange that, you get B equals A over T root 2H over G. So then percentage uncertainty of B is going to be A is being divided by T. Whenever you're dividing, you add the percentage uncertainties together. So percentage uncertainty of A plus the percentage uncertainty of T, plus, because that then is getting multiplied by H, which has an square root of H, which has an uncertainty. 2 and G are just constants, so there's no uncertainty with them. So because that's getting multiplied by, then it is plus the percentage uncertainty of root H, and we'll deal with that square root over here somewhere. Right. Now, substituting in here, so I've sort of jumped over here a little bit because there's extra steps, because we don't actually have Hey, do I know we do? I figured out A. Sorry, I said earlier they give you that. They don't. I figured out the value of the cross-sectional area here. So A equals pi d squared over 4. Substituted in the diameter, got me that area. If you can follow this, good luck. Oh, sorry. So the first thing I did here for this is to find the percentage uncertainty of A. Because A is calculated using pi d squared over 4, then it's going to be whatever the percentage uncertainty of D is multiplied by 2, because that is the rule. If something has a power, you multiply it to get the uncertainty. So here's my working for that. The percentage uncertainty of D is the absolute uncertainty of D over the value, and that has come from up here, multiplied by 100. So the percentage uncertainty of D gets me this, which then means I can calculate the percentage uncertainty of A. Percentage uncertainty of A is going to be 2 times the percentage uncertainty of D, because D is squared in this equation. That gets that, and you'll see I've drawn wee boxes around here. It's because there's like 50,000 numbers everywhere, and I needed to know what bits I had to pick out to put into my final equation. So this is one that we end up using, so that's why I've drawn a box around it. Then the next one I need is the percentage uncertainty of T, so I've worked out that. So that's just the absolute uncertainty over the value of T, and that has come from up here, multiplied by 100, so that gives me the percentage uncertainty of T. Again, I've drawn a box around it because it's important, I'm going to need it. And then the percentage uncertainty of root H is what I'm going to need next. So I did my percentage uncertainty of H, which is the absolute uncertainty divided by the value multiplied by 100, gets me that. So it's 0.8% for H, but it's root H that I need, which means I have to multiply by half, because root H is like H to the power of a half, and same as with D squared in the area equation, the rule for uncertainties is that you multiply by the whatever value the power is. So the percentage uncertainty here, 0.8 multiplied by a half, that's because of that square root, gets me that. So that is where these numbers have come from, which gets me this percentage uncertainty, right? And that's the final answer. So let's have a look at what the marks are for. So there's 6 marks for this. There's 1 mark for getting the cross-sectional area of the container. There's 1 mark for calculating the value of B. There is 1 mark for getting the percentage uncertainty of T, 1 for getting the percentage uncertainty of A, 1 for getting the percentage uncertainty of root H, and then 1 for adding all your percentage uncertainties together at the end, and the right ones getting added together. Okay. Right, question 4. So the loudness in decibels was measured at various distances D from a speaker. The loudness was measured using a decibel meter, just shown here. There's the results. So at a distance of 0.1, the loudness was measured at these 3 separate times, and then that's the average. Then it gives you the equation. So the loudness of a sound measured in decibels is related to the distance away from the source of the sound, as shown by this equation here. Now in the photocopy that I have, this plus wasn't very obvious, but because you're working from the one straight from Say's website, it should be fine in yours. But that's the equation. See, I didn't tell you there's logs. There's always one log question. Tells you all the information. So P and L naught are constants. P is the power, L naught is the threshold intensity of hearing, and that's the value of it. So part A, calculate values for log D in meters. This here, I don't know if you are all clear on this yet. I have been correcting it for you, but this is how you need to write whenever you're doing logs. You don't just put no unit. I know log of number has no unit, but you don't just put no unit, you put log, and then in brackets you say what you're taking log of and in what unit. So log of D in meters. Anyway, so calculate values for log D and insert them in the final column of table 4.1, then and record your values to 3 decimal places. So 2 marks, 1 for your values and 1 for all being to 3 decimal places. That's them. We should all have the exact same numbers for that. B, part 1. Draw a graph of L against log D on the grid. Choose a suitable scale for the axes, plot the points and draw the best fit line for the points. So there's 5 marks for this. I'll just show you what that's what my graph looks like there. So the values that they've given us do work to give a nice straight line. 1 for having your axes scaled correctly. Remember, that means your points have to take up at least half of the available space, and nothing dodgy with broken axes or anything. So like for example, see the way here I have started at 30. If I had put 0 and then 35 and then 40, I would lose a mark. Whereas if I put 0 and then a squiggly line and 35 and 40, that would be fine. But it's better just to not put the 0 on at all. I always just start from a number, and then they'll not take marks off you for that. So have your axes scaled correctly. Labels correct. Your points plotted gets you 2 marks, and then your best fit line gives you 1 mark. If you have your axes the wrong way around, then you lose a mark. There we are. Part 2. Use your graph to find a value for the power P of the sound. So we end up, well, this is what the 3 marks are for. I'll do that first. So the reading off your y-intercept correctly, putting your intercept equal to 10 log of P over 2 pi L naught, and then finding a consistent value of P. So let's see how we knew that was what we did, because this here is in the form y equals mx plus c. So this is the y-intercept here, right? So I got on mine 42. Everyone's will be slightly different, and that is fine. I will be working out, and the examiner will work out what your equivalent P value is. So 1 mark for finding your intercept, 1 mark for putting it equal to this, so really for this line here, and then 1 mark for correctly calculating what value of P that gives you. Part 3, explain, oh, there's someone at the door, hold on. The Amazon package, wasn't even for me. Rachel, I've forgotten where we were now. Part 3. Yeah. Right, explain how, using your plotted points, the absolute uncertainty in your value of P could be obtained. So you need to draw an extreme fit line, then read your new intercept, and then calculate the extreme P. So doing all this again for your new y-intercept. Well, actually, sorry, you don't have to do it. You're just explaining how. So you need to say that this is what you're doing. So read the new value of your intercept, calculate the extreme P value, and then say that you can get the absolute uncertainty. It's just the difference between the 2 P values, your original one and your new one. Yeah? Right, let's look at question 5. So the resultant interference pattern from 2 sound waves is displayed on a CRO screen, and the display is shown in here, which is just over the page. On the same CRO screen with the same settings, it's used to display the individual sound waves. Oh, I remember doing this one. It's a stinker. One of the sound waves that cause the interferences is shown in 5.1b, and then on 5.1c we have to draw the second wave. We'll look at what the marks are for, and then I'll show you mine. It'll be easier to show you on the actual graphs. So there's 1 mark for having a point at the origin at the start. I think that's what I mean by that. There's 3 marks for the points. You're plotting 5 points, so there's half a mark each really, and then it gets rounded up. And then you lose a mark if you haven't actually drawn a curve onto what you plotted. So let's have a look at this. So this here is the resultant of the 2 curves. Now, see, whenever I was doing this, I totally did not believe my values. Like it didn't come out like I was expecting it to, but waves are not my forte. So you can see here I've marked on wee points. This was whenever I was calculating it. So this graph here is equal to this graph plus this other one. So really you're like taking this away from this one to figure out the point. So I'll just pick out a few of them to show you what I did. So this was at 3, and the first one was at 3. So 3 take away 3 gives us 0. So that's why I've plotted a wee point here at 0. I'll try and pick out nice ones. Let's look at this point here. And obviously I have done other ones, but I'm not going to go through every single point here. You'll be here all day. So at this point, the height of this one was at 2. and the height of this one is at 0.4. Yep, so 2 take away 0.4 is 1.6. So the corresponding point down here has to be at 1.6. Do you see what I'm doing? And I did that just for every bold line really on it. So let me see. Let's look at this one. So this one here is at -1. So the sum of these other two has to give us -1. The corresponding point on this one is at -2.8. So that means that, let's see if my mental maths will work, -2.8, and what's I have to get to? -1, so it's going to be 1.8. Yeah. So yeah, this one here has to be plotted at 1.8. Okay. So that is what your graph should end up looking like. But it's not, I honestly was naively enough expecting it just to really be a mirror image of this, but it doesn't, so it doesn't end up like that. So it's tricky enough, this. Okay, so part B, part 1. Right, so the wave in figure 5.1b, so that is this one. It's not this one, it's this one here. Has a frequency of 1500 hertz. The length of the trace shown is 10 centimeters. So that means that this is 10 centimeters. What is the time-based setting on the CRO and given an appropriate unit? So the first thing that I figured out was from the frequency, I can figure out the time period of the wave, t equals 1 over f. That gets you that. So that means that this is equal, or sorry, that's how much of the wave that is, or how much time has gone by for this. Now, 10 centimeters is equal to this much of a wave, and this is 3/4 of a wave. It's not a full wave. So that's what I've done here. So 10 centimeters is 3/4 of, this is the time for one complete wave. So 3/4 of that gives us 10 centimeters. So I've just, from here to here, I've just figured this out, which means 1 centimeter is equal to that, and that's what the time base is, what 1 centimeter is equal to. So it's 5 times 10 to the -5, and the unit is seconds per centimeter. Right? Now, this is the stuff that I always think you lot are better than me at, because you do all the wave stuff with Mrs. Turner. This is the only time I do the wave stuff, so I'm always a wee bit iffy on it. So if I can do it, that means you can do it. Right, last part. Calculate the frequency of the wave you have drawn here. So, let me see. We figured out that 10 centimeters is this many seconds, because, well, that's just straight up there. And that is half a time period, because on this wave, so this is 5.1c, it's talking about this one, that is half of a wave. So now that we know that this is 10 centimeters and we have the time that that represents, we know that that is half of the time period of that wave. Does that make sense? It makes sense to me. So that means the time period is going to be just double that. And then once you get the time period, you can get the frequency using f equals 1 over t, and you get 1000 hertz. So the marks on this one are 4. 1 for recognising that the 10 centimeters is equal to half of a time period, and then 1 for working out the time period, and then 1 for getting the frequency. Okay, hopefully this is helpful. Hopefully, I don't know that I did any much explanation here, but hopefully it's helpful to see like the emphasis I'm putting on things rather than just seeing this screen here. Who knows? See you soon. Bye.